Hello everyone and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. All right, so this is where we stopped in the previous class. We were talking about the precipitation sequence in different aluminum alloys, and we have been covering all the heat treatable alloys one by one. So the last one that we covered was the 7000 series alloys. That's the aluminum, zinc, magnesium alloys. And here we have seen that the main precipitate, the main strengthening precipitate is the eta prime. Okay, but the formation of such precipitates depends on the quenching rate also, right? Because the quenching rate might affect vacancy formation and all that. And since we are talking about movement of atoms, formation of atom clusters, and so on, the precipitation sequence may be affected due to that. Okay, so in this particular alloy, in order to form this eta prime precipitates uniformly, you need to first form the GP zones also homogeneously. Okay, and in certain scenarios, particularly if you have low vacancy concentrations, then the GP zones will form at lower temperature. They will form homogeneously rather at lower temperature, and therefore at times it is better to carry out a two-stage aging process for the 7000 series alloy rather than a single stage process. This will take care that the GP zones form first when you age it in the first stage at a lower temperature, and once the GP zones form and get stabilized, you can raise the temperature for the precipitation to occur, and that's when your eta prime precipitates will form. And now that the GP zones have already formed, there is no difficulty for the formation of the eta prime precipitates all over the place uniformly. Okay, so that's the objective of having this two-stage aging process in this set of alloys. Okay, so we are going to continue on this, and now let us have a look at some of the alloys in this particular series and their properties as well. You might know that the aircraft fuselage and many other parts are made of aluminum alloys because of their high strength to weight ratio, because these are light alloys, so you can obtain a very high strength to weight ratio. And this is one property which is particularly useful for the aerospace sector, and that is why a large part of the aircraft is made of aluminum alloys. And the alloy which is widely used particularly in the fuselage of the aircraft is this 7050 alloy. It has all the favorable properties needed for that kind of application, where it has to not only be lightweight but has to satisfy the other structural requirements in terms of the mechanical properties. For example, the fatigue resistance and such properties, all those can be satisfied by this alloy. Okay, and that is why this is an alloy which is used in making the fuselage of the aircraft and some other parts also. So let us have a look at this alloy. First, let us have a look at the composition. So this is basically having 6.2% zinc, 2.2% magnesium, 2.3 copper, and some amount of zirconium as a grain refiner. Okay, and this is used in T7 condition, although it can be peak aged to maximum hardness in T6 condition, but to satisfy some of the property requirements, it is better to use in T7 condition, because in T7 condition, apart from the strengthening and the other requirements for the mechanical properties, it also gives rise to a good corrosion resistance, right? So in this condition, if you look at the strength, the yield strength is around 450 MPa. And as I said, it also provides a good corrosion resistance. And if you look at the properties in T6 condition of this particular alloy, then you have somewhat higher strength, because T7 is kind of overaged. So in the peak aged condition, if you see, this will provide a yield strength of 505 MPa. And the other favorable properties that this alloy exhibits, apart from the mechanical properties, is the low quench sensitivity. This is to say that the alloy can be easily quenched, and you can form the supersaturated solid solution all across the thickness of the material, right? So the thickness is not really a big factor in this case, because there could be materials which have high quench sensitivity, and for such materials having high quench sensitivity, it may be difficult to quench it uniformly all across the thickness if you have a higher thickness or a bigger section, right? But in this case, that is not a problem because of the low quench sensitivity of the material, and therefore thick forging can be easily quenched in water. And in fact, in order to have a better low quench sensitivity for these alloys, this can be quenched in hot water or warm water. Let us talk about one more alloy in this series, and this is 7005. The composition of which is as follows. This has 4.5% zinc, 1.4% magnesium, some amount of manganese, and some chromium and zirconium. This will give you 290 MPa yield strength in T6 condition. And this kind of alloys are used in automotives, parts, and things like that. So they are basically for ground transport applications. Right, so this will bring us to the end of the 7000 series. So we'll go on to the next one, that is the 8000 series alloys or the aluminum lithium alloys. You can say this is the lightest among the aluminum alloys because of the presence of lithium here, which is the lightest metal that you can think of among the commonly available metals that you have, or the alloying elements that you have, which can be added to aluminum. And therefore, 1% addition of lithium can reduce the weight by 3%, can reduce the density by 3%. And this is one reason, why in 80s these alloys really attracted a lot of interest because of their lightweight and also high strength. So they could provide very high strength to weight ratio, and people thought, now these are the alloys which can bring revolution into the transportation industry, particularly for the aerospace sector. Okay. So before we go to that as to why it did not really take off even after having this kind of favorable properties, we'll come to that. But before that, let us see the precipitation sequence of this particular alloy series. Okay. So here, you have lithium. So you have a lithium bearing precipitate forming, and the sequence is quite simple here. The precipitate directly forms from the supersaturated solid solution, and the precipitate that you get over here is the delta prime precipitate, which basically has a composition of this Al3 Li, and delta is the equilibrium phase. So as I said, these precipitates form very fast directly from the supersaturated solid solution. So it also means that the activation energy for their formation is low, and therefore you do not really need the formation of GP zones as the precondition for forming this kind of precipitates, right? So that's why you get these precipitates directly as you start the aging process after quenching. And these precipitates have got an ordered structure. And therefore, the hardening or the strengthening mechanism in these alloys comes from the order strengthening that we discussed before, right? So here, as we have discussed, when dislocations move through these ordered precipitates, because of the ordering, antiphase boundaries will form, and formation of those boundaries will make it more difficult for the dislocations to move through the precipitates, and as a result of that, the strength will increase. Okay, so we have already discussed that before. And now if you look at the ordered structure of this particular phase, this is basically Al1 2 type crystal structure. The prototype of which can be found in these copper gold solid solutions, copper gold ordered alloys. Having a similar stoichiometry, as you could see, 3:1, right? between the two atoms that you have. Here it is lithium and aluminium, and in this case it is between copper and gold. Okay, so this kind of atomic configuration can form an ordered structure over a long range. So this is basically an FCC kind of structure, where the corners are occupied by the lithium atoms, and the face centers are occupied by the aluminium atoms. And the lattice parameter for this particular structure is around 0.403 nanometer. So you can see, this is very close to the parent metal aluminium, and therefore the misfit strain is low for such precipitates. So you cannot really expect too much strengthening to come from those elastic strain kind of mechanisms, right? Because there is not much of mismatch between the precipitates and the parent metal in terms of the size. Okay, so therefore there has to be some other mechanism, and as I said, in this case it is the order strengthening mechanism which will operate for this particular alloy. Okay, and these precipitates in terms of the morphology have a spherical shape. And this shape remains spherical throughout the entire aging period. So let us again have a look at the order strengthening which occurs in this case. The strengthening comes from the antiphase boundaries when the dislocations move through the precipitates and when the precipitates are sheared by the dislocations. So these are precipitates, which can be sheared by dislocations. So while the dislocations are moving through these precipitates, like many other precipitates which are actually non-deformable or not shearable by dislocations, and this kind of non-deformable precipitates will actually stop the dislocations till the stress is raised and the dislocations break free, right? But in this case, as the dislocations encounter the precipitates and as you keep deforming the material or as the stress is raised, that dislocations can actually shear through the precipitates, right? So these are shearable precipitates. So once that happens, the dislocations will tend to move only along these planes where this shearing can easily take place, right? And as a result of that, the deformation will be localized. And this will reduce the strain to fracture, or in other words, the ductility will come down. So this is the reason, why this kind of alloys exhibit a low ductility and also low fracture toughness. And this was the major reason as to why these alloys did not really take off even after having favorable properties, particularly with regard to the strength to weight ratio. This was due to this low ductility and fracture toughness. So this is something which could not be overcome, and as a result of that, although they attracted a lot of attention in the beginning, ultimately, this whole area of aluminum lithium alloys started to decline as people started to realize that this low ductility and fracture toughness cannot be overcome, right? So you cannot really use this kind of alloys in critical applications like aerospace and aircraft and things like that, simply because of the fact that they have low fracture toughness. And now if you look at the equilibrium phase delta in this particular alloy, unlike the previous alloys, the equilibrium phase does not have the same composition. Delta is having a composition where aluminum and lithium is 1:1 and not 3:1. Okay, so this is the composition or the formula for the equilibrium phase delta in this case. And the structure of delta, the crystal structure is of B32 type, which is basically the NaTl structure. Where you have two diamond cubic lattice penetrating each other. Okay, so two types of atoms that you have in ratio 1:1, they will form two lattice of a similar type, which is diamond cubic, and these two lattice will be interpenetrating. Okay, so that's the way to define the structure. So if you look at this particular phase now, the structure of this, it will be like this. Lithium in a diamond cubic lattice. And to describe the position of aluminum atoms, you can simply take them in between the lithium atoms. So all these blue circles that you see now will be the aluminum atoms. Right, so this is how the structure can be defined. As I said, this is basically the B32 or NATL type structure. All right, so I'll stop here today, and the rest of the things that we have on this topic will be taken up in the next lecture. Thank you for your attention.